Hi, everyone. Hope the weekend went well. We are very close to the end here, so just hang in another week or two, and it'll be riding off into the sunset here. Um, man, it's been a wild ride. Hope that you've been able to maintain, keep up with your classes. I know that this has been a challenge. Thank you for all the effort that you've put in. Uh, I know that I know from experience that there's a lot of extra work, things that you've had to do that are outside of the norm. So I just want to encourage you that um, God can use all of this to help shape your character. So we just trust that that's precisely what will take place. Um, last time we talked about confidence intervals in the context of utilizing the standard normal distribution. And the lecture before that, I had talked at length about the T distribution and how that would also be brought to bear in the context of confidence intervals. So this lecture is going to delve into that. I'm somewhat hopeful that this may not be a very long lecture because I just want to make sure that you really absorb this last bit before we get into hypothesis testing. The plan moving forward is, in all likelihood, I will midweek send out the final, and you'll just have basically like a week to work on it. I'm hoping to not impose on you more than I have to. I'm trying to let you have as open a schedule as possible during finals week, and I think this might be one way to accomplish that. So just be on the lookout for that. Know that that's coming, and my hope is to grant you as much flexibility as possible as it pertains to this class. At least you're doing a great job, you guys, with keeping up on stuff, uploading things. So hopefully this one last thing will be doable for you as well. Okay. All right. So let's go ahead and jump in here a little bit. Want to remind you of a couple of things. Okay. So first of all, we were talking about, I just kind of want to scroll back through here real quick so that you can see some stuff. We did several cases for confidence intervals. Okay, the first case was the case where the population distribution is, known to be normal, or it really appears to be normal. Okay, and we know that we actually knew the standard deviation of the population, which is typically not the case, but it could be. Okay, and we came up with the following formula for the confidence interval. Okay, and what is this Z alpha over 2 thing we're talking about? So first of all, you get the sample mean, X bar, and you go down by Z alpha over 2 times sigma over the square root of n, and up by that amount. X bar is in the middle. The interval itself is random. The middle of it's moving around, but the width is staying the same in this case. Sigma is fixed. Okay, and so is the sample size. Okay, what is the Z alpha over 2? Well, it comes from this. It's the 1 minus alpha is the level of confidence. Z alpha over 2 and minus Z alpha over 2 are the kind of the cutoff points. You have these two tails where you have alpha split between them. So alpha over 2 in each. Okay, and we came up with some critical values. That's what those things are called in various contexts in the last lecture. Okay, so this, and then we had the one-sided confidence intervals. This is where all we care about is like either an upper bound for the population mean or a lower bound for the population mean. And by the way, we're only talking about population mean here. So this is a confidence interval for the population mean. Okay? And the idea is, if I were to create a whole bunch of these intervals with various samples of size n, then 1 minus alpha times 100% of the time, those intervals would contain the population mean, which is a fixed quantity, by the way. Okay, so it's not really proper to say the probability that mu belongs to the interval is 1 minus alpha. That's technically true, but it's confusing because mu isn't random. The population mean is not random. Okay, so we like to think about the interval being random. Okay, and then we had these upper and lower bound intervals where all we care about is one side, and there we put all of the alpha level. You remember we call it alpha level. All of the alpha level goes into the tail, into one tail. Okay, so we constructed those. Okay, and again, X bar is a thing that's random. And then we got to case 2, where if the samples, okay, so here the population distribution is not necessarily normal, and we don't know the standard deviation of the population. Okay, so in that case, as long as n is large enough, we can invoke the central limit theorem, and n greater than 30 is usually sufficient. And we can invoke the central limit theorem, and we get these formulas where we replace sigma with S, the formula for the sample standard deviation. Now the thing is, S is also random. Okay, so S and X bar are both random in this case. So here the width is also random. So as well as the center X bar, okay? Because that S is a random variable now, and that's going to determine the width of the interval, right? If S is big for my sample, it's going to make it wider. If S is small, it's going to make it smaller. So now I have like a kind of moving, shrinking, and stretching, shrinking and stretching random interval moving around. And the percentage of time that those random intervals are going to contain the population mean is 100 times 1 minus alpha if we construct it according to these formulas here, which look just like what we did in the other case with sigma replaced by S, the sample standard deviation, because we no longer know the population standard deviation. Okay, we did some examples with that. Okay, here we kind of tried to, last time toward the end, we stared at this for a minute and said, what is the confidence level of these things? And we sorted that out. Okay, and the third case is the one that I want to concentrate on today. Okay, it's the population distribution, again, not necessarily normal. Okay, before what bailed us out is n was beyond 30, and we invoked the central limit theorem, and we knew that we could use z's, right? Look, all of these, we basically use the z distribution. Okay, well, what in the world are we going to do if our sample size is below 30 and we don't know diddly squat about the distribution? Okay. And incidentally, we also don't know the standard deviation, so we're just totally kind of up a creek without a paddle, so to speak. All we do is we take the sample. For whatever reason, we're unable to get a sample that's large enough beyond the 30 threshold. That does happen from time to time. Maybe you send out a poll of some kind and you just don't get that many respondents. Okay, and so you just have what you have. That's it. So what do? Well, it turns out that in this case, you can invoke a weaker version of the central limit theorem that will use a distribution that is not quite the standard normal, but it's the t distribution, which we already talked about a couple lectures back. I was trying to prime the pump for this case right here. Okay. So remember, this is just kind of to remind you of what's happening. You're actually going to make this big, just now that we're kind of into the full presentation here. Okay. So the t distribution depends on the parameter nu. Okay, again, this is the Greek letter nu, not mu, nu. Okay, it's like the Greek n. It says n, it makes the sound n phonetically, like our English n. Okay, that's called the degrees of freedom. okay? And the degrees of freedom for a sample is nu equal to n minus 1, right? It's always 1 less than the sample size, okay? I'm not going to get into the nitty-gritty details about what's going on with that. I will just basically say, okay, if I were to tell you what the sample mean is, like if I said the sample mean is 50, and I just and then I said, okay, you know the sample mean is 50, and then suppose that all the first 49 data values were random. Well, if I told you what the sample mean was, what it equals, and then the first 49 data values were random, then the 50th data value would be forced to be whatever it would have to be to make the sample mean 50. So the first n minus 1 things could essentially be random. But the nth thing, if I tell you what the sample mean is, the nth thing would be determined by what the sample mean is, whereas the other 49 would be totally random. So those 49 of 50, or n minus 1 out of n things, would be free to be whatever they wanted. And then if somebody told me what the sample mean was, that last one wouldn't be free. Okay, so the degrees of freedom is 1 less than the sample size. That's really the essence of what's going on. But to really get down into the nitty-gritty, we'd have to do some pretty highbrow statistics, theoretical statistics. Okay, so each of these t sub nu curves is bell-shaped, just like the normal distribution, centered at 0, but it's more spread out. It has fatter tails than the standard normal. But as nu goes to infinity, the t sub nu curves tend toward the normal distribution, the standard normal distribution. We talked about that last time, okay? Yeah, okay, so you see that picture there, you have t sub 5, so that's 5 degrees of freedom. Look, it's kind of a little bit more squatty, the tail's fatter, and then the tail is shrinking down more and more the higher the degrees of freedom go, and those curves kind of approach the standard normal from below, and the tails are kind of approaching the standard normal from above. Okay, so that's how that works. Of course, the area under each one of those curves is always 1 because it's a density. Okay. Okay. So a definition of a critical value here. Now remember, we had these z sub alphas and z sub alpha over 2s things going on here. So the critical value is the value t sub alpha nu. Now, I mean, just to let you know, we had something like that back here. Okay. Well, it was in essence this thing right here, these z sub alphas, z sub alpha over 2. Okay. So the probability that the standard normal is greater than or equal to z sub alpha over 2 is equal to alpha over 2, right? Okay, so these are also referred to as critical values. Okay, critical values. And it'll be clear later on when we do hypothesis testing, or the last couple lectures, why we use this term critical values. Okay, but this terminology is going to come back, now with the t distribution as well. Okay, so same concept back over here. Okay, the critical value is the value t alpha nu, such that the probability that t, okay, so by the way, t is just distributed as t sub nu, okay? So it's a t distribution with nu degrees of freedom. Okay, the probability that t, the random variable, is bigger than this value is equal to alpha. And this picture kind of says it all. Okay, that picture is what's going on here. There's the t nu curve. Probability that t is beyond that is equal to alpha. Okay, and this is just a fact. The statistic t equal to x bar minus mu divided by s over the square root of n. Okay, which we've seen that come up before as sigma over the square root of n in the case of the normal distribution. That's the standard deviation of x bar. Okay, has a t distribution with n minus 1 degrees of freedom. In other words, this thing right here, okay, this thing right here is distributed as T with n minus 1 degrees of freedom. So in other words, mu is equal to n minus 1, okay? So that has the T distribution, and that's really helpful because then we can come up with a formula for the T distribution. So for instance, let me just, you know, since that's true, think about it for a minute. What is the probability that x bar minus mu over s divided by the square root of n is between T alpha n minus, or let me say alpha over 2 n minus 1 and greater than or equal to negative T alpha over 2 comma n minus 1. Okay, well, by definition, you're going to have alpha above, by symmetry, or alpha over 2 above this thing. Okay, there's going to be, right, alpha over 2 above this cutoff. And then what about this guy right here? You're going to have alpha over 2 below. Okay, so the probability that this thing is between these two values, since it has the T distribution within minus 1 degrees of freedom, this is equal to, is equal to what? Is equal to 1 minus alpha. And then I am telling you, you just rearrange this thing in here. Let me get a different color here. You rearrange this junk in here, and what you're going to get is that the probability that x bar minus what? T alpha over 2 comma n minus 1 times s over the square root of n is less than or equal to mu is less than or equal to x bar plus T alpha over 2 comma n minus 1 times s over the square root of n. This is equal to 1 minus alpha. Okay, so that means the probability that mu is in that random interval that I just drew right there, or that I just wrote right there, the probability that mu is in that random interval is 1 minus alpha, just like it was, right? So this formula is almost exactly the same as it was before, except like z alpha over 2 has been replaced by this T alpha over 2 with n minus 1 degrees of freedom. Now I have to pay attention to the degrees of freedom because I have a different distribution for every different degree of freedom, okay? Okay, so here are the formulas. 100 times 1 minus alpha percent confidence intervals are, and I just kind of justified that first one right there. So x bar minus T alpha over 2 n minus 1 s over square root of n, and the x bar plus that amount. Again, look, I have some randomness going on here. First of all, T alpha over 2 n minus 1, that's not random. N isn't random, but this and this, those are random, right? So these guys are random, okay? So again, the width is random, the center x bar is random, and the width is random. Here, okay, right? So the center, like where this interval is moving around based on what my sample is, my sample mean. And then and the width is also random. That's also based on my sample as well. S, remember, includes things like x bar, and you take the differences of squares of x, the data values and x bar, add up the square differences, divide by n minus 1, take the square root. That's your sample standard deviation. And this is the upper bound version and the lower bound version. Okay, same sorts of things that we had before. Okay. Okay, so just as a little exercise here, what do I want here? So for this guy, what am I looking for? Well, I'm looking for this. So first of all, this is going to be the 15 degree of freedom curve, and T sub 0.1, 0.15. So what is that? So this is T sub 0.1 and 15, it has the property that how much area is there above this? Well, 10%, which means how much area is there below this thing? Well, 90%, right? So this T sub 0.1 with 15 degrees of freedom, this is really the 90th percentile. Okay, we've talked about this before, but it's always good to kind of refresh our memories on this thing. And what about this guy? What about this guy? Okay, well, again, what curve am I looking at here? And again, these T distributions always have 0 in the middle. Okay, well, this is the curve with 25 degrees of freedom, 25 degrees of freedom. And what is happening? Well, T sub 0.05, 25, well, it has the property that I have 5% up here, which means how much do I have below? Well, that means I have 95% below. Okay, so this guy is the 95th percentile. Okay, the 95th percentile. So T sub 0.1, 15 degrees of freedom, and T sub 0.05 with 25 degrees of freedom. So the first one is the 90th percentile. Second one is the 95th percentile, right? So let's think about that. We'll look up a couple of those, okay? So, or we'll look up those two things in a couple of ways, actually. So one of them is to kind of use this table, okay? So look, here's this T distribution. I'm over here in Wikipedia, again, which I said has a great breakdown of the T distribution. Somewhat surprising. So here's 15 degrees of freedom right here, okay? 15 degrees of freedom and one-sided, so 90%. Okay, so here this means 90% below the value in this column. There's 90% below it. Okay, two-sided, what that means is, you know, whatever that number is, you know, you're going to have a particular percentage above it, and you're going to have symmetrically the same that percentage below it, and essentially this thing is going to capture the middle 80%, which means I'm going to have 10% to the right of this value and then 90% to the left of it, but then also going to chop off, you know, 10% from the left tail also. So this thing says, right, 15, this thing right here, the reason I'm looking at this is the 90th percentile, okay? This is the 90th percentile. Right, so this guy right here is the 90th percentile. The 90th percentile. Okay. 1.341. 1.341. Okay. So let me just say, you know, I'll write this up here. T sub 0.1 and 15 degrees of freedom is equal to 1.341. Okay, what about another one? So the other one was the 25th percentile. Let me just erase this junk here. Okay, erase this junk. Okay, so here we go. The other one was the 25 degrees of freedom. And by the way, notice what happens with this table. It starts to not care after 30. Why? Well, because at that point, you might as well be using the stinking normal distribution. You know what I'm saying? Look, these numbers are hardly changing anymore beyond this, okay? So you might as well just invoke the full scoped central limit theorem and say, well, I'm going to use the standard normal table. But if you really want to be super careful, you could still use the T distribution. But notice they're skipping degrees of freedom at this point. And I think down here they even say like infinity. And these right here are just the Z values, right? These guys down here, these are just Z values. They come from the standard normal, right? So that makes for a pretty helpful thing, yeah. To have that all in one table, basically. Okay, So I have t sub 0.1 with 15 degrees of freedom. Let's go to 25 degrees of freedom. And I wanted the 95th percentile, which would be this. Remember, that guy right there. Okay, so I want t sub 0.05 comma 25. Okay, equals what? Well, I go down to 25, and I think it's right here. Let's just make sure. Just want to make sure I'm not highlighting the incorrect thing. 1.708. Okay. Another way I could have come up with those is in Excel. Okay. This is me. I'm preparing for something here in just a minute. But I could have also said, all right, let me just write this. T sub, 0.1 with 15 degrees of freedom. What's that equal to? Well, you go equals. You know that if it's 10% to the right of this thing, then it's 90% to the left. So you go T distribution inverse. Okay, what's the probability I want? So 90%, 15, and we hope and pray that's going to be 1.341, and it is. Okay, what about T sub 0.05? 25. Okay, well, that means I have 95% to the left. Okay, so what's that going to be? Well, equals T distribution, or T inverse. Okay, what's my probability? 95% to the left. Degrees of freedom, 25. I get 1.708, which is exactly what we got before. So we see it in two different ways. Okay. All right. So let's go back over here. There we go. Okay. So determine the critical value for a two-sided confidence interval, one-sided confidence interval, if the confidence level is 99% and the sample size is 5. Okay, so here I have n equal to 5, which means degrees of freedom, right? Which another letter for that is nu, is 4, one less than that. Okay, so the degrees of freedom is 4. If the confidence level is 99% for a two-sided situation, 99% for a two-sided situation. Okay, so if I want 99% confidence, what's going on here? Okay, so first of all, we have a very small number of degrees of freedom. So this is going to be a T sub 4 distribution. Okay, so two-sided, I want 99% confidence. Okay, so I want 0.99 right in the middle. Okay, which means that I want to have 0.005 down here, and same thing down here, 0.005. Okay, so that means I want T sub 0.005 comma, right, 0.005 comma 4, right, 4 degrees of freedom. And then of course this is just going to be the negative of that by symmetry, negative T sub 0.005 comma 4. Okay, so in the two-sided situation, that's what we have going on. What about the one-sided situation? Well, in the one-sided situation, again, same distribution. Okay, remember 0 is right in the middle, 0 is right in the middle. This is T sub 4. Okay, the one-sided situation, what's happening? Okay, so that means that I'm going to have 99% just to the left. Okay, and what about that? So it's going to be T sub 0.01 comma 4. Okay, so that means I have 1% right here. 0.01. Okay, I'm not splitting 1% anymore. It's just purely 1%. Okay, and I'm just going to do the upper one, of course. So this is like an upper bound situation. A lower bound situation, I would just reflect this across right here. So I want T sub 0.005. Okay, so let me see, T sub 0.1 comma 4 equals something. and T sub point oops. I'm at 0.014 and 0.005 comma 4 equals something. Okay. All right. So let me erase some of this stuff. So gonna let me erase it. Yeah, here we go. Okay, erase this stuff so that we can go figure it out. Yeah. All right. So let's go. Okay, so I go to the table. Okay, so let's see. T sub, so 99.5, they have that in here as well. Okay, 0.005 to the right means 99 point, or you know, 0.005, that's point, right, 0.995 to the left. This means 0.005 to the right, okay? I only have 4 degrees of freedom, so I'm gonna have 4.604 for that one. 4.604 is the critical value, or negative 4.604 if I wanted to do a lower bound confidence interval, okay? And in the other situation, or sorry, no, that would be the two-sided, right? So that would be the two-sided one. Now, what about the one-sided one? Well, the one-sided one is just a straight up 99% to the left of this thing. Okay, so that's 3.1% above. So that's 3.747. So just to let you know, so this is two-sided. Oh no, sorry. Jeez. Okay, that is one-sided. Okay, so that's one-sided confidence interval, and this guy right here is the two-sided one. Okay, two-sided confidence interval. Okay. Is that right? So 99% below, just the 1% above, 3.74. Yeah, one-sided. For the two-sided, you want a 99% confidence interval. You're gonna have to go up a little bit further to 4.604, and then negative 4.604 on the left would give you your two critical values. Okay. We could have done that in Excel also, of course. Okay. So going back in here. So let's see here. I'm gonna erase this screen. The success of a certain procedure depends on various properties of human nasal, the human nasal periosteum. For a sample of 15 adults, the mean failure strain was 25, and the standard deviation was 3.5. Okay. So, for example, of 15 adults, so here we have n equal to 15, which means nu equals 14, the degrees of freedom, yes? And we have x bar, just writing down everything we know. X bar is equal to 25, right? So 25 is literally going to be percentage points. And the standard deviation, okay? So, and this was a sample standard deviation. So S is equal to 3.5. S is equal to 3.5. Assuming a normal distribution, and by the way, this right here, you don't actually need this. The sample size is already smallish, right? So you know that you're going to be leaning toward the standard normal, or you're going to be leaning towards the t distribution, unless you happen to know the sample standard deviation, which we, or the population standard deviation, which we don't. Okay. Then you're going to be, with such a small sample size, you're going to be leaning towards a t distribution anyways. Okay, so we don't really actually need this assumption about normality. Assuming a normal for failure, assuming a normal distribution for failure strain, estimate true average strain in a way that conveys information about precision and reality. Okay, and they haven't told me anything about this, but basically what they're saying is give us a confidence interval. So you would go x bar plus or minus T alpha over 2, okay? So this would be two-sided, a two-sided estimate for the mean. So it'll be X bar plus or minus T alpha over 2, 14 times S over the square root of 15. Okay? And you would just have to determine what the critical values were, and you would be done. That's it. Okay. So you just have to find the critical values, T alpha over 2, 14, like we've been doing before, depending on what your alpha level was, which is confidence level 1 minus alpha. Confidence level 1 minus alpha, alpha level alpha, right? So those are the those are the two terms that you use over and over. And this is the formula for your confidence interval, and you just give it as an interval with the minus part on the left and the plus part on the right. Okay. Okay, so I'm not going to go any further than that on that one. Okay. So next, an automotive supplier of interior parts places several electrical wires in a harness. Pull test measures the force required to pull spliced wires apart. Customer requires that each wire spliced into the harness must withstand a pull force of 20 pounds. Let X equal the pull force required to put 20 gauge or to pull 20 gauge wires apart. Okay. Assume that the distribution of X is normal. Okay. And again, you wouldn't have to have that be true necessarily if you were going to use the T distribution. I just want to emphasize that. The following data give 20 observations of X. And I've actually put these data into Excel for us to mess with on the last slide here. Okay, so there's 20. So N is equal to 20 here. Okay. Find point estimates for mu and for X bar. Well, of course, for mu, you're just going to do, I said the answer. For mu, you're going to use X bar. For sigma, you're going to use S. Those are your point estimates. Okay. So they're just flat out point estimates. Find a 99% one-sided confidence interval for mu that provides a lower bound for mu. Okay. So I want a 99% confidence interval. One-sided. So this is going to be X bar minus, this is a lower bound, minus T, okay, since it's only one-sided, I would put all of the alpha there, okay, and my degrees of freedom are 19, and I would multiply this by S over the square root of 20, okay? So that would be my lower bound. And then I would give my confidence interval as this, comma, infinity, right? So comma, infinity. Okay, but that first part right there is the important part. And what's our alpha? What's alpha equal to? 1%. You don't split it between two sides on this one. So it's just 0.01 with 19 degrees of freedom. Okay. All right, so let's see here. Let's go do this. Okay. Okay, so let me clear this and like rewrite what's going on here. Okay, so we want X bar minus T sub 0.01 with 19 degrees of freedom times S over the square root of 20. Okay. And so what is our cutoff point here? So T sub, let's see here, T sub 0.01, comma, with 19 degrees of freedom. And again, I could go use the table if I wanted. Okay, I could go use the table if I wanted, but I can also just use Excel right here. So if 1% is to the right of this thing, if 1% is to the right of this thing, what percentage is to the left? Okay. Well, you go T inverse, right? It's going to be 99%. 0.99. What's our degrees of freedom? Well, 19. Okay, 2.539. Okay, so 2.539. And of course, I could have also gotten that over here. Okay, where is 19 degrees of freedom? Let's see here. 19 degrees of freedom. 99% to the left. Okay, it's this column right here that I already have an item highlighted in. Okay, 19 degrees of freedom. Is this the right one? Right, 99%, 2.539. I think that's what we had over here. Yes. Fantastic. Okay. So what's X bar going to be? X bar equals, well, you can just go equals average. Okay, and what you do is you just have to highlight all of these things right here. All 20 of these things. Okay, so there's our X bar. Okay. And what is S? S equals, so this is a sample standard deviation. Okay, and what is S going to be? Well, equals, start typing standard deviation. This one's for a population, which is not what we have. And this is for a sample. Okay, and this automatically does everything for us. Okay, of course, we know how to compute this thing by hand, but might as well let Excel do the heavy lifting for us. Okay, so what's the 99% lower bound confidence interval for, let me just, lower bound confidence interval for mu. So what is it going to be? Well, so let's go equals X bar, which is this, minus, okay, we said it's got to be this number right here, oops, minus this number times S divided by square root, okay, Excel knows how to do square roots, square root of 20. There's right there, 24.059, okay? And let me just say comma infinity, okay? So, if I wanted to be real clever here, I'll actually write it right here. So it's 24.059 comma infinity would be the lower bound confidence interval for mu. Okay, just delete this part. And there it is. That would be our lower bound confidence interval. So we're 99% confident that this random interval contains the population mean. Okay, 24.059. So let me write this down right here. So 24.059. 24.059, okay, comma, infinity. So lower bounded one-sided confidence interval for this thing. Now that's interesting because if you stare at this for a minute, let's just look back at this and we'll be done here in just a sec. Find a 9% confidence interval for mu that provides a lower bound for mu, so 24.059. Remember the setup of this problem was that we want this thing to, a customer requires that each wire spliced in the harness must withstand a pull force of 20 pounds. Okay. And it seems like the average is likely for the population to be much higher than that. Actually, it's very likely with 99% confidence to be above 24.059. So that's good. Given what it is that we actually desired here. And we kind of could glean that from this data right here. I mean, very rare, we didn't have a single example of one that was, dangerously close other than the 20.81. All the rest of them were well above that 20-pound limit, okay? And so we are 99% confidence that the true population mean is in this random interval that has as a lower bound 24.059, okay? All right. That is it. That is it for confidence intervals. Now we are going to take this information from the confidence interval section, and we're going to wrap up our discussion of statistics by looking at forming hypotheses, things that we think are true, and learning how to test those using statistics and actually using confidence intervals to rigorously test whether our hypotheses are likely to be true or not. Okay, so that's to come. Hope you enjoyed this. Please continue to hang in there, and I will see you soon.